Hello everyone, welcome to lecture 6 on differential calculus. Today we are going to talk about one of the most important applications of derivatives, that is its use as a tool for finding optimal solution to problems. For example, uh, a manufacturer would always like to minimize the production cost or maximize the profit, or you can say that how much minimum material is required to make a uh, cold drink cylindrical can of certain volume. So all these comes under finding the optimal solutions. That means finding the maximum or the minimum under certain conditions. So today we are going to learn about how to locate and identify the maximum or minimum values of a function from its derivative. Okay, and we will also talk about the mean value theorem. So let us first see what we mean by maxima and minima. That means what are extreme values. Okay, so extreme values of functions. Let f be a function with domain D, then f has an absolute maximum value on the domain at a point C if the function value at C is greater than equal to all function values for all x in the domain. Okay, so f of C will be the absolute maximum value if this value is greater than equal to all the values of the function for all x in the domain. Okay, and uh, and an absolute minimum value of d at a point C. So this function has a absolute minima at C if the function value at C is the smallest value, if it is less than equal to all the function values for all x in the domain. Okay, so so the value is maximum if it is greater than equal to all other values, and it is the minimum if it is less than equal to all other values for the function. Okay, maximum and minimum values are called the extreme values of the function f. Okay, so extreme values is a common name given to maximum or minimum, and absolute maxima or absolute minima are also referred to as global maxima or global minima. Okay, so we can call absolute maxima or we can also call it global maxima. Okay, similarly absolute minima is also called as global minima. Okay, so here both how the function is defined and what is the domain of the function, both plays an important role. Okay, and extreme values can vary depending upon the domain even when function rule is same. Okay, so we'll just see, say for example, say you are given a function rule that y is equal to x square is the function, and its domain is given minus infinity to plus infinity. Okay, so that means there is a curve y is equal to x square which is unbounded. Okay, minus infinity to plus infinity is the domain. Then you can see that this function has no absolute maximum value. As x goes to plus infinity, this keeps on growing. Okay, and similar on the other end, but it has an absolute minima at x is equal to 0. Okay, so x equal to 0, y value is 0, so that's an absolute minima for this function. Okay, now see how domain is important. If I keep this function rule, but if I change the domain. Okay, say for example function is y is equal to x square and domain is closed interval 0 to 2. Okay, so function is defined from 0 to 2, this curve y is equal to x square in blue, and the values at 0 and values at 2 are also included. Okay, so then you can see that this point is the maximum value. So at x is equal to 2, the y value equal to 4 is the absolute maxima, and at x0 y0 is the absolute minima. So this has both absolute maximum as well as absolute minimum. Okay, let us see another case. If I domain if I further change the domain for the same function. Okay, so I use that domain is uh, open at 0 and closed at 2. then in that case again we have this y is equal to x square function, where at x is equal to 2 the value is defined, but x is equal to 0 is not part of domain. Okay, so then it has the absolute maximum here. At x is equal to 2 value is 4, but there is no absolute minimum now. Okay, so it has got only the maxima. Okay, no minima. And similarly, say I again define this same function but with both ends open. Okay, so domain is open interval 0 to 2. So now the y is equal to x square, it is not defined at x is equal to 2, it is not defined at x is equal to 0. So function is in open interval 0 to 2, so it has no extrema, there is no maximum value for this, there is no minimum value for this function. Okay, so domain is very important in this case when we deal with maxima and minima. Okay, so both function and domain they play an important role. Okay, so one thing we noticed here is that we found that there is both absolute minima and maximum when there is a closed interval. Okay, so in this case we found that there is a absolute maximum as well as absolute minimum. Okay, so here you see that there is a closed interval and there is a function which is continuous. Okay, so this is exactly what our first theorem is, which is the extreme value theorem. Okay, so extreme value theorem says that if a function is continuous on a closed interval ab, then function attains both absolute maximum value, say capital M, and an absolute minimum value, say small m, in this closed interval. Okay, so if function is continuous on a closed interval ab, then that function has an absolute maximum value as well as a absolute minimum value in that interval. Okay, so and mathematically we can say that there are numbers x1 and x2 in this interval a to b, such that function value at x1 is the absolute minimum value small m, and function value at x2 is the absolute maximum value capital M, and function for all other x lies between this minima and maxima. Okay, so again remember there's both continuity of function. Okay, as well as the interval is closed interval, both are important. Okay, so we already talked about that this if we have open interval, uh, then uh, you may not have absolute maxima or absolute minima. Okay, and okay, continuity is also important here. Okay, so I'll just show you that for example this function uh, which is not continuous at x is equal to 1, so it will not have a maxima. Okay, or minima. Okay, in this particular case it does not have an absolute maxima. Okay, so when y is x for all x greater than equal to 0 and strictly less than 1, and y is 0 when x is 1. Okay, so y is equal to x. Okay, from 0 up to less than 1, and at at x is equal to 1 y value is 0. So there is a discontinuity uh, at x is equal to 1, and you can see then there is no maximum value. Okay, so continuity is also important, and that the finite interval ab should be closed. Okay, now we define the local or relative extreme values. Okay, so we already said the absolute maxima is when function value at that point is the largest for all x in the domain, or we have an absolute minima if the function value at c is less than equal to fx for all x in the domain. But then uh, we may have many local maximas or many local minimas for a function. Okay, so let us define this first. A function f has a local maximum value at c within its domain d if the maxima means the function at c must be greater than. Okay, so f of c must be greater than equal to fx for all x belongs to domain lying in some open interval containing C. Okay, so in some neighborhood of C, okay, if I construct an open interval containing the point C, if this holds, then we say that point C is a point of local maxima. Okay, so instead of uh, all points of the domain, but we are talking about the points of the domain which are in the neighborhood of the point C. Okay, so an open interval containing the point C. Okay, and similarly a function has a local minima or local minimum value at C within its domain D if the function value at C is the smaller value than all values in the small neighborhood. That means the function value at C is less than equal to fx for all x in the D lying in some open interval containing C. Okay, so let us see what exactly we mean. Say for example, you are given this curve, okay, of a function y is equal to fx. Then you can see that these points are points of local maxima. Okay, uh, here if I consider this to be a C point, then the value of function fc here is the greater than equal to all function values in the small neighborhood of this. Okay, so if I consider interval from here to here, okay, an open interval containing the point C, then the corresponding values of function will vary from here up to here. Okay, and so this f of C value will be greater than all fx value of the domain containing lying in this open interval. Okay, so this becomes a local maxima. Okay, similarly this is again a local maxima because it satisfies the same condition that the function value at this point is greater than the function values of all points in the small neighborhood, okay, or in an open interval containing this D. Okay, so this is also a absolute maxima because if I treat all local maximums, then this value is the largest of all the local maximum. Okay, so basically absolute maxima is also a local maxima. Okay, and if you know all the local maximums, then you can compare all the local maximum values and you can find out the absolute maximum value. Okay, similarly this point is a point of local minima because the function value here is less than equal to the function values in the neighborhood for all x in the domain and lying in some open interval containing this point t, okay, of the domain. Okay, so f of c is less than fx, okay, for all x in the small interval containing the point e. Okay, so this acts as a local minima. Similarly we can find all the local minimas, okay, and then we can compare all local minimas and see which one is the smallest of all. Okay, then we can declare that as a absolute minima. Okay, so this way we can calculate local maximas and local minimas, and then by comparing those maximas we can find absolute maximum, and comparing the minimas we can find the absolute minimum value. Okay, so now I define an important theorem which says the first derivative theorem for local extreme values. Okay, so the previous theorem that we did is the extreme value theorem, which says that when function is continuous and bounded in a closed interval, then it will have a maxima as well as a minima. Okay, uh, but if we have to locate those maximas and minimas, okay, then either we have to check for all x values in the domain the function values and see where it is maximum and where it is minimum. Okay, so this test is very important because then this tells us that we only need to investigate few values to find function extremas. Okay, so we only need to check the few values which will tell us whether there is a maxima there or minima there. Okay, so this theorem says that if function has a local maximum or minimum value at an interior point C of its domain, okay, and if function derivative is defined at this point c, then the function derivative at c must be 0. Okay, so this theorem says that if function has a local maximum value or a local minimum value at c, where c is the interior point of domain, and the derivative of function is defined at this point, then the derivative at this point must be 0. Okay, and this theorem cannot be reversed. That means if you find that at some point c the derivative is 0, then it does not mean that will have a local maxima or minima at that. Okay, only if it has a local maxima or minima, then it and derivative is defined at c, then you can say that derivative at c must be 0. Okay, but the converse is not true. That means if you prove that derivative at some point is 0, that does not mean that that point is a point of local maxima or local minima. Okay, for example, say if you are given a function f(x) is equal to x cube, then you know that the first derivative f dash x is 3x square, and the derivative will be 0 at x0. Okay, because 3x square is 0 at x0. Okay, but that doesn't mean that x0 is a point of local maxima or point of local minima. Okay, if you plot x cube curve, you will see that x is equal to 0 is neither a point of maxima nor a point of minima. Okay, so derivative equal to 0 does not imply that it is a point of maxima or minima. But yes, if a function has a local maxima or minima at c and the derivative is defined at c, then definitely the derivative at c must be 0. Okay, so we will prove this result. Okay, first, so suppose that f has a local maximum at x is equal to c, and if it has a local maximum at c, then that means the function value of c must be greater than equal to all other function values for all x near to c. Okay, in this neighborhood of c. Okay, so if I consider any open interval containing c, okay, then the function value at c must be greater than equal to all function values for all x belongs to that interval. Okay, okay, then since c is an interior point of domain, okay, it is given. Okay, and f dash c is defined by. Okay, so we know the how to calculate the derivative using the limit formula. Okay, this means that the right hand and left hand limits both exist at x is equal to c and equals f dash c. Okay, because the derivative exists. Okay, and we know by definition that derivative will exist if the right hand this limit exists, and by limit definition this limit exists if both the right hand and left hand limit exist, and it is equal to the derivative function derivative at c, because they are equal. Okay, so we'll now prove that the derivative cannot be positive, and then we'll prove that the derivative cannot be negative, and both immediately implies that derivative must be 0. Okay, so first we take the left hand limit. Okay, and because the function value at c is greater than equal to its point of maxima is greater than equal to fx. Okay, and for left hand limit x minus c is less than 0. Okay, because x approaches c from the negative side. Okay, so that means x values are smaller than c. Okay, so the derivative definition, which is limit x tends to c from the negative side f of x minus fc over x minus c, this is greater than equal to 0, means the derivative values uh, cannot be negative. Okay, and this is because fx minus fc is less than equal to 0 and x minus c is less than 0. Okay, so it becomes greater than equal to 0. Okay, so by left hand limit we can prove that the derivative value at c cannot be negative. Similarly, if we calculate the right hand limit, then uh, again this is already there that the fc values are greater than equal to fx, but if x approaches c from plus side, that means x lies to the right side of c, so x will be greater than the value of c, and so x minus c will be positive. Okay, so the derivative value, which is equal to this limit value, the numerator is less than equal to 0 and denominator is positive. Okay, so this ratio as limit approaches is less than equal to 0, that means the derivative at c cannot be positive. Okay, so left hand limit says the derivative cannot be negative, right hand limit says derivative cannot be positive, but derivative exists, uh, so left hand and right hand limits must be equal, and which is only possible if the derivative is exactly 0. Okay, so thus result is true when f has a local maximum at the interior point x is equal to c. Okay, so for local maximum this is the proof. Okay, similarly for local minima we can proceed with the same steps and we can easily prove the only change you will find that for local minima fc is less than equal to fx for all x in the small interval containing the point c. Okay, so this inequality will be reversed and accordingly these will change and you will find the same result. Okay, so I'm not proving the second similar argument you can use, and you can prove that when f has a local minimum at interior point x is equal to c and the conditions satisfy, then derivative at c must be 0. Okay, so now I'm going to prove uh, give you some definitions here, and first definition is about the critical points. Okay, so it says that an interior point of the domain of a function f where the derivative is 0 or derivative is undefined is a critical point of the function. Okay, so we call all those points of the domain as the critical points, the x values as critical points where derivative is 0 or the derivative is undefined. Okay, and then we can utilize these points to find whether there is any point of local minima or local maxima as at these points or not. Okay, so how to find the possible points for extrema? As I said that if you are given a function or a curve, then there is no need to check at each point of the domain the function value and compare them to find maximum or minima. Okay, so we only need to investigate few points to find the function extremas, and to do that what we have to do is that we have to find all the critical points, and whatever are the endpoints of the domain, only the extreme values can exist on those points. Okay, so the only places where a function f can possibly have an extreme value, local or global, are the interior points where derivative is 0 or interior points where derivative is undefined. So these two combinedly we said are critical points, and also the local maxima or minima can occur at the endpoints of the domain, so we also need to consider the endpoints of the domain of the function. Okay, and then if you know all the critical points and the endpoints of the domain, then you can check the function value at those points, and you can compare. Okay, compare those values to find the largest function value and the smallest function value, which will tell us what are the points of local maxima and what are the points of local minima, and what are the points of absolute maxima and what are the points of absolute minima. Okay, so so then method is very simple, that you given a function, uh, you calculate its derivative. Okay, and then you solve to find the critical points. That means you put f dash equal to 0 and find the critical points. Okay, and also check all those points where derivative is undefined. Okay, so all those will become critical points. Note down the endpoints of the domain. Okay, and then evaluate the function value at all the critical points and endpoints, and then compare the function values. Okay, so the largest function value will tell us the point of absolute maxima, and the smallest function value will tell us the point of absolute minima. Okay, Say, for example, find the absolute maximum and the minimum values of the function fx is equal to x square, okay, on given this domain -2 to 1. Okay, so we know it is a continuous function and it's a interval which is closed interval. So by theorem there will be an absolute maxima as well as an absolute minima. Okay, so now how to calculate that using the method is that you calculate the first derivative of this, and we know f dash x or df by dx will be equal to 2 times x. Okay, so then you can calculate the critical points by substituting that equal to 0. So 2x equal to 0 gives x is equal to 0 as a critical point, and uh, okay, so we get x is equal to 0 as a critical point of this, and the derivative is 2x, so there is no point in this domain where the function is not defined. Okay, so this is the only critical point. Okay, only interior critical point. Okay, and we are given two endpoints, -2 and 1. Okay, so what we have to do now is evaluate the function value at x is equal to 0. Okay, that is at the critical points, and then evaluate the function value at the endpoints -2 and 1, and then compare all these three values. Okay, so at the critical point f of 0 is 0, at the endpoints f of -2 is -2 square, which is 4, and at the endpoint 1 function value is 1 square, which is 1. Okay, so we now have these three values. We can compare and see that 4 is the maximum value and 0 is the least value. Okay, so the point of absolute minima is 0 and the point of absolute maxima is -2. Okay. So this was example 1. Okay, let us take another example. Say find the absolute maximum and minimum values of function fx is equal to x raised to power 2 by 3 on the interval -2 3. Okay, so again method says you calculate the first derivative of this. Okay, so the first derivative of x raised to power 2 by 3 is 2 by 3 and the third root of x. Okay, so then find the critical points. Okay, so there is no value of x which makes derivative 0. Okay, but there is a value of x in the domain which makes the derivative undefined, that is x is equal to 0. So x is equal to 0 is a critical point. Okay, because derivative is undefined at this point, and there are two endpoints -2 and 3. Okay, so we have to evaluate the function value at critical point. Okay, so at x0 function value is 0. Okay, and at the endpoint, so function value at -2, so we'll put -2 here. Okay, and function value at 3. Okay, so put x as 3. Okay, so f of 3, then compare all these three values. So you can see that this is the maximum value and this is the minimum value. Okay, so we get that point of absolute minima is x is equal to 0 and point of absolute maxima is x is equal to 3. Okay, right. So now I define another theorem here, which is known as Rolle's theorem, and it says that suppose that y is equal to fx is continuous over the closed interval ab and differentiable at every point of its interior. Okay, so open interval ab. If the function value at a equals the function value at b, then there is at least one number c in the open interval ab at which the uh, derivative at c is 0. Okay, so there is at least one point, there can be more than one point, but there is at least one point c where the slope of the function is horizontal, okay, parallel to x-axis. Okay, so say for example there is a curve this. Okay, and there is a point a, there is a point b, and the function value at a and function value at b are equal. Okay, so this is, if this is true, then uh, under the condition that the function was continuous and is differentiable at every point in the interval interior of AB. Okay, then there are points, or at least one point, where the slope is parallel to x-axis. Okay, the derivative at this point is 0. Okay, so here there are certain condition. One is that the function has to be continuous in the closed interval, and the function has to be everywhere differentiable in the open interval. Okay, so both conditions are very necessary. If any of these conditions do not hold, then this theorem fails. Okay, so both continuity in closed interval and differentiability in open interval are important here. Okay, and as a counter example, say uh, if there is a discontinuity at the end point. Okay, say at the end point here a, here the function is not continuous. Okay, then you can see that even if function value at a and function value at b are same, but there is no point inside where the slope is horizontal. Okay, so this continuity at endpoints is important. Similarly, continuity at an internal point is important. Okay, so if there is a discontinuity at any point x naught, which is a interior point, then again you can see the function a and function b are same. Okay, at a and b the function values are same, but there is no point c in the open interval ab where the slope is horizontal. Okay, so continuity is important in the closed interval. Okay, so and then differentiability is also important in the open interval. Okay, say as a counter example, uh, if the function is continuous, but there is a point where function is not differentiable in the interior, then you can see that because the derivative does not exist here, so there is no point in the interior where the slope becomes horizontal. Okay, even when the function value at a and function value at b are equal. Okay, so both that the continuity in closed interval as well as the function has to be differentiable in the interior of the interval ab. Okay, both these are important and necessary conditions. Okay, so now we will prove this theorem that function is continuous in closed interval and differentiable in open interval, and if the function value at a and b are same, then there is at least one point where the slope is horizontal. Okay, so to prove this result, first is that you are given that the function is continuous. Okay, and so being a continuous function, it assumes absolute maximum or minimum value in the closed interval by extreme value theorem. So we talked about this theorem in this lecture earlier, that if a function is continuous in a closed interval, then it will have both absolute maximum and absolute minimum. Okay, so because it is given continuous in closed interval, so it will assume the absolute maximum value as well as absolute minimum values by this theorem. Okay, now if it has a maxima and a minima, okay, in this closed interval, then maxima and minima by the derivative theorem, they can occur only in on the points which are given by these three conditions. Okay, either you will find the maxima or minima in the interior point where derivative is 0. Okay, or you will find the maxima or minima at the interior point where derivative does not exist. Okay, or you will find the maxima or minima at the end points of the domain. In this case the endpoints are a and b. Okay, so only these three cases are there. Okay, so either the interior points which are critical points or the end points. Okay, so we already said that we calculate maxima and minima only on the critical points or end points. Only there the maxima or minima are possible. Okay, now the second condition does not fit this theorem, because it is said that function is continuous and the derivative and the function is differentiable in the open interval ab. Okay, so if function is differentiable in the open interval ab, so then there will be no interior point where derivative does not exist. Okay, so the second possibility ruled out. Okay, so the only cases are the first case where the derivative is 0, or the endpoints of the domain, in this case a and b. Okay, so the second possibility is not there because the derivative of the function is defined at every interior point. Okay, now we take the first case that if the either the maximum value or the minimum value, either of them, if they occur at the interior point. Okay, so if either the maximum value or the minimum value occurs at the interior point, say C between A and B, then by first derivative theorem, the derivative at C must be 0. Okay, so the result of Rolle's theorem is automatically satisfied. Okay, so if the uh, maxima minima occurs at interior point, then automatically the derivative is 0. Okay, and this for at least one point C in AB, and Rolle's theorem will be satisfied. The other possibility is that neither the maxima nor the minima occurs in the interior. So, but this function assume both maxima and minima. That means both maxima and minima will only occur at the endpoints. Okay, so if both the absolute maximum and the absolute minimum occurs only at the endpoints, then because the function value at a and function value at b, they are equal. Okay, and if maxima is at the endpoint and minima is also at the endpoint, then function value of a, if it is maximum, then function value of b must be minimum, or if f of a is minimum, then f of b must be maximum, but they are equal. Okay, so it is the only possible way to have this could happen is that the function is a constant function. Okay, that means the function value at all x in the open interval must be equal to fa and fb. That means all the points lie on the horizontal line. Okay, so in that case also the Rolle's theorem is satisfied because now we can choose C to be any point between A and B, because the values are horizontal and so slope at each point is 0. Okay, so therefore the derivative at x is 0, and C we can choose anywhere in the interior of AB. Okay, so Rolle's theorem is satisfied in that case also. Okay, so this is the proof of Rolle's theorem. Okay, now we are going to prove one important theorem here, which is known by as the mean value theorem, and it says that suppose that y is equal to fx is continuous over the closed interval AB and differentiable at every point of its interior AB, then there is at least one point C in AB at which uh, the f dash C is equal to fb minus fa over b minus a. Okay, so uh, this theorem, in this theorem, the condition on Rolle's theorem, which was that fa equals to fb, that has been relaxed. Okay, so uh, this theorem, if you look carefully, then if fa equals fb, then the numerator will be 0, and it immediately gives us f dash c is 0. Okay, so if that condition is imposed, that fa is equal to fb, then the mean value theorem immediately reduces to the Rolle's theorem. Okay, and the other point is that mm, and the derivative at c, where c is an interior point, is uh, the slope at c, and we know what is fb minus fa over b minus a. Okay, is the change in function value to change in the domain value, so it is like delta y by delta x. Okay, so it's the slope of the secant. Okay, so this theorem says that there is at least one point C where the slope becomes parallel to the slope of the secant. Okay, so geometrically, the mean value theorem says that somewhere between A and B, the curve has at least one tangent parallel to the secant joining A and B. Okay, so if you have a function uh, and in the closed interval AB function is continuous, and in the open interval it is differentiable at every point, then the slope of secant is parallel to the tangent for at least one point C in AB. Okay, so there is at least one point C inside this open interval AB, such that the slope at that point is parallel to the slope of the secant. Okay, so this is a important theorem. Okay, so first we'll prove this theorem. Okay, so the let there be a curve y is equal to fx. Okay, and say there is a point A and there is a point B, so that the corresponding points are marked as A and B. Okay, so the slope, the equation of the secant line AB, we can write by the point slope equation as y is equal to y1 plus the slope of secant times x minus x1. Okay, so y is equal to y1 plus derivative or slope times x minus x1. Okay, so the at a the function value is f of a. Okay, so y1 is f of a, then slope of this we know is fb minus fa over b minus a. Okay, times x minus x1. X1 is a. Okay, so we can write the equation of this secant line, and then we define hx to be difference between fx and gx. Okay, so the vertical difference between the graph f and g at x is hx minus fx minus gx. Okay, and because the two curves meet at or crosses at a and crosses at b, so at a and b the difference is exactly 0. Okay, so if we plot this curve it will look like this. Okay, at a the hx value is 0, at b the hx value is 0. Okay, so you see that the function hx satisfies all the conditions of the Rolle's theorem. Okay, and here we can substitute gx to be this. Okay, so we can write hx, which is fx minus gx. By substituting gx as this, we can rewrite this as this function. Okay, and it satisfies all the conditions of Rolle's theorem, because the function fx is continuous in closed interval AB, and gx is also continuous. So that tangent line, uh, uh, then it's a secant line. Okay, so the difference is also continuous in the closed interval AB. Okay, and because the function fx is differentiable, okay, and gx is differentiable, so difference is also differentiable in the open interval AB. Okay, so all the conditions of Rolle's theorem are satisfied because the endpoint values are also same at a and b. H of a and h of b are 0. Okay, so that you can also check by substituting x as a here and x as b here. Okay, so because then I say that it is continuous on AB, differentiable on AB because both f and g are, and also ha hb are 0. Okay, so the all the conditions or hypotheses of Rolle's theorem are satisfied, which immediately means that there is at least one point C inside the open interval AB such that the uh, h derivative at C must be 0. Okay, so that's what Rolle's theorem says. Okay, so now we can use this. Okay, and so we if we calculate the derivative of h from here, and then if I put x as c and then use this equation, then I can calculate from here my mean value result. Okay, so let us calculate the h derivative x will be equal to f derivative x. Okay, uh, this is a constant number, so its derivative is 0. So minus this is a constant number times derivative of x will be 1 and derivative constant will be 0. Okay, so it will give f dash x minus this ratio. Okay, so h dash x we can easily calculate as f dash x minus the this ratio. Okay, and then we can easily write what is h dash c, which will be f dash c minus this. Okay, and because h dash c is 0, So we can write 0 equal to this, and so we can calculate that f dash c must be equal to the slope of secant. Okay, so there is at least one point c in the open interval ab such that the slope at c is uh, exactly parallel to the slope of the secant. Okay, so we can also interpret it in this way that if we think that this number is the average change of the function over AB, and so the uh, change at a point is the instantaneous change. Okay, so then the mean value theorem also says that at some interior point the instantaneous change must be equal to the average change over the interval. Okay, so this is also an interpretation for this result. Okay, say for example if a car is accelerating from 0 and takes 8 seconds to go to 352 feet, its average velocity for the 8-second interval is. Okay, so if there is a car which is accelerating and reaches 352 feet in 8 seconds, then the average velocity, okay, we can calculate as fb minus fa over b minus a. Okay, and because at a fa is 0 and a is 0, so it is simply fb over b. Okay, so it is simply 352 by 8, which is 44 feet per second. Okay, so the average velocity, and then the mean value theorem says that there is at least one point c in the interval 0 to 8 such that the instantaneous uh, velocity or the speedometer will show the same speed at that instant. Okay, so there is at least one point where the car speed is 30 miles per hour, which is equal to actually this value 44 feet per second. Okay, so this is one example. Say I take one more example here. Say find the value or values of c that satisfy this equation. Okay, where the function is this quadratic polynomial in uh, 0 to 1. Okay, so here the function is given. Okay, so if we calculate the derivative of this function, so that will be 2x plus 2. Okay, and then we can calculate the function value at both endpoints, so f of 0 and f of 1. Okay, so f of 0 is -1 and f of 1 is 2. Okay, and then if there is a point c inside 0 and 1, uh, then f dash c will be simply 2c plus 2. Okay, so if we substitute all these values back here, we can calculate the point c. Okay, so 2 plus 2c plus 2 on the left hand side as f dash c, and fb is 2, f of a is -1, and b minus a is 1 minus 0, which is 1. Okay, so we can easily substitute all the values here, and we can calculate c. Okay, so c is half. Okay, so if we plot this uh, quadratic in a graph, okay, this blue curve. Okay, and so if we calculate the right hand side, that this secant. Okay, and there is at least one point c which is half, so at x value half here, there is a tangent which is parallel to this secant. Okay, so this was the how we can use mean value theorem to solve numericals. Now I will close this topic with two corollaries, and first is that if the derivative of function is 0 at each point x of an open interval ab, then function must be a constant function for all x in ab, where c is a constant. Okay, so this result that uh, says that only the constant functions can have a derivative 0. okay, at each point. Okay, so we'll prove this result that let x1 and x2 be any 2 points in open interval AB with x1 less than x2. Okay, then the function fx satisfies all the hypotheses of mean value theorem on the closed interval x1 x2 because the derivative exists. Okay, so function is differentiable in this interval, and because function is differentiable, so it must be continuous. Okay, so the function is continuous and it is differentiable, then it satisfies all the hypotheses of mean value theorem. So that means there must be at least one point C inside the x interval x1 and x2, okay, such that f dash c must be equal to fx2 minus fx1 over x2 minus x1. Okay, now since it is given that derivative is 0 for all x, okay, so immediately derivative must be 0 for the point C because C also lies in that interval. Okay, so f dash C must be 0. Okay, and which immediately gives that fx2 must be equal to fx1. Okay, and because x1 and x2 are arbitrary points of this interval, so that means the function values at all points of the domain must be same. That means function must be a constant function. Okay, so this is a proof of corollary 1. Okay, the second corollary is that if the derivative of function f equals derivative of function g at each point x in an open interval AB, then there exists a constant c such that fx must be equal to gx plus constant for all x in the open interval AB. That is, the function difference is a constant function in AB. Okay, so this is also an important result in the sense that what functions will have equal derivatives. Okay, so only those functions which differ by a constant, okay, will have equal derivative at each point in an open interval AB. Okay, so the proof of this is simple. Let hx be this difference function. Let hx be fx minus gx, and at each point x in open interval AB, the derivative of this difference function then we can calculate because fx and gx are differentiable, so is hx. Okay, so h dash x is equal to f dash x minus g dash x, but the derivatives are equal, so this difference must be 0. Okay, so h dash x is 0, and by the previous corollary, okay, the uh, if derivative is 0 for every x, then the hx function must be a constant function. Okay, but hx is fx minus gx. Okay, so this difference must be constant, or fx must be equal to gx plus constant. Okay, so this proves our second result. Okay, that uh, the derivative of two functions will be equal at each point x only if they differ by a constant, or if one can be written as a constant as second function plus constant. Okay, so I close this lecture here. In the next lecture we'll continue with the applications of derivatives, and we'll learn about monotonic functions and how to calculate or check the concavity of the functions. Okay, have a very good day.